Hi everyone, this is a quick instructional video on your 4.4.3 physics lab, which is on optics. So you've learned a little bit about optics so far, and this lab kind of gets you to practice the optics equations. Okay, so again, you are doing the dry lab, and these are the two equations you're going to be doing or using to do your calculations. So first of all, you have this 1 over f equals 1 over di plus 1 over do. Hopefully at this point you already know what these mean, but they do define them a little bit here. So remember, f is your focal length. Di is the image distance, in other words, the distance that the image forms from the lens. And do is the object distance, or in this case, in this picture, the object is the light source. So how far away is the light source from the lens? Okay. Now the image forms on the screen. Okay. So wherever you move the screen to get a clear in focus image, that's where the image forms, right? So that's the distance to the lens. It's wherever the screen is. The second equation that you have here is, we call this a magnification equation, but it's actually a proportion of heights to distances. So it's hi over ho, which is image height over object height, equals negative, don't lose this negative here, negative di, which is the image distance, over do. Okay, so that's just a simple proportion. So this kind of goes through the procedures. Where do you place the object and what do you get in terms of distances and heights? Okay, so the experimental results are given to you here. Your job is to complete this table by doing some calculations. So to calculate the di, you are going to use this equation, the 1 over f equals 1 over di plus 1 over do. Okay, you'll notice the information they're giving you. This is your f, right? So 1 over 25 equals, this is your do for this trial, 54. This is when it's greater than 2f. So greater than 2f means if the focal length is 25, double the focal length, or 2f, would be 50. And so in this case, they have put the object beyond double the focal length, or beyond 2f. So they've put it at 54 centimeters. All right, so you're going to do 1 over f, or 1 over 25, equals 1 over di, and you're solving for the di here. You're solving for the image distance, plus 1 over do, or 1 over 54. Okay, so you're going to do that calculation. It is easiest to do the calculation using the x to the minus 1 button on your calculator. If you don't know where that is or how to use it, just shoot me an email. I will help you out. And then you're going to do the image height. So to calculate the image height, you're going to use this proportion, right? You now have the di because you just calculated it. You have the do from right here, 54. You have the ho, the object height. Okay, the object height is right here. And you're going to solve for the hi, or image height, and you're going to put that answer here. Okay, now you're going to do that for a do of 50 centimeters using these numbers. You're also going to do it for 42 centimeters. Okay, once you have the calculated values, you're going to go down here and you're going to do it again, this time with a mirror. Okay, so you have the same values. You're going to use the same equation. Okay, you're going to use this same equation, mirror and lens, same equations, and you're going to do your calculations for the second table. All right. Then you're going to do some analysis of your data. Okay, so the first question says, what happens to the height of the image formed by a convex lens as the object moves closer to the lens? So you guys, what I'm looking for here is not just these values, but can you show me how you did this? Like, show me your calculation method, because a lot of times what happens is you put numbers in here and they're wrong, And I can't give you partial credit because I can't see your work. If I could see your work and I can find your mistake, then I can give you partial credit. So make sure you show me your work for how you got the numbers in these two charts. Okay, and then you're going to look for some patterns. What happens to the image height as it moves closer to the lens? So closer to the lens means moving down this chart, 60, 50, 46, 54, 50, 42. That's getting closer to the lens. Okay. What happens to the DI as you move closer to the lens? How do your calculated and experimental numbers compare? Create a graphic organizer to show the different images created by the convex lens and concave mirror. So this is up to you. How you want to organize your information is completely up to you. The only requirements I have is that it is organized, it is easy to understand, and easy to look at. Okay? In part 3, what happened to the brightness of the light when you put the polarizing filter over the light source? So you're going to be looking at this right here. And then you're going to draw some conclusions. How do images formed by a concave mirror compare to those formed by a convex lens? Real, virtual, what kind of image is formed by a concave mirror? So you should know the difference between a real image and a virtual image. A real image is an image that can form clearly and in focus on a screen. A virtual image is not a real image. It does not form on a screen. A virtual image is simply a mathematical solution to something that is physically impossible, right? So an image doesn't form, the rays do not meet on the correct side of the lens or mirror, but they do meet if you project them backwards. That's a virtual image, okay? A virtual image does not exist in the physical world. It's only just a mathematical solution. And then you explore further. Imagine you moved the object to a distance closer than f from the lens and try to find the image on the screen. Why can't you find a clear picture? So you should be thinking about how do the light rays refract through the lens and will they meet? How would you refine the experiment? And then this you don't have to do because it has to do with a ripple tank. Okay? All right, so if you have any questions, just shoot me an email and we can jump on Zoom and work through it together.